Okay, so the recording has been started, guys. So, good evening. Uh, Welcome to the demo session of Everything Metallurgy for GATE 2023. Okay, so as discussed earlier, as mentioned earlier, today I'll be taking a couple of topics which will be served as a demo purpose. So, the topics which I'm going to cover are the phase diagrams from the physical metallurgy, and then the requested topic from mechanical metallurgy, which is Mohr circle. Okay, so Mohr circle has been asked by a few of you guys in the group, so that's the reason why I put it in this. Okay, so we have these two topics lined up for today. Okay, and if you have any doubts, you can always unmute yourself and stop it, and you can ask your questions, or the chat box is always there. You can just put in your queries in the chat box. Okay, and yes, the people who are already joining the group, please do uh, you know join the call. Okay, just joining the conservation is a conversation is not sufficient. You have to actually join the call. Okay, so I just put a quick message in the chat box. Yeah, so let's get started. So we all know that we have one complete year lined up for 2023 from now, and that's how we are going to plan our full length 1 year live sessions. Okay, so many, I mean, before directly jumping into the demo session itself, a few queries which I get by many students recently. Okay, so this will be a comprehensive 1 year course, okay, which starts from March 14th. Okay, so the course will be starting from March 14th. Okay, and you'll be having everything covered in this. Like, you will be getting one-on-one live interactions, like how we are discussing. We'll be getting a complete test series, and of course, if you miss any live session, you will be given the access to watch the recording of the same session on the website. Okay, and yeah, this is what it is, and let's get started with the topic: phase diagrams. Okay, and yeah, one more thing. Many people asked about that, if this course helped for any PSUs or any examinations like bar, any interviews. And let me tell you, many people actually follow our videos, our courses for their college placements too. Okay, many of the people actually used these videos to crack good interviews, not only in the campus but even off campus placements, using gate or without gate too. Okay, so that's about a few FAQs which I wanted to just discuss. But now, coming back to the topic itself, the first topic for the today: phase diagram. So what is a phase diagram? Phase diagram is nothing but a simple graph. Okay, it explains some relationship between the phases. Is it? So as I told you, it is nothing but a relation between two phases which are in equilibrium. Okay, so this word is important. Equilibrium relationships can be understood using the graphical representations. And what are these called? Phase diagrams, or these are also called as equilibrium diagrams. Okay, these are also called as equilibrium diagrams. Now, so what is an equilibrium? So for that, you all know that for a chemical reaction, what we say, when the forward reaction rate is equal to the backward reaction rate, we say that that particular reaction or that particular system is in equilibrium. Similarly, let's say if I have two phases AB, okay, with whatever concentrations, we are not going in detail into that, but these two phases are in equilibrium. That means some x percentage of A is in equilibrium with some y percentage of B at a given temperature, at a given condition. What is that condition called as? Equilibrium. That means they coexist. Equilibrium in the sense they are stable. Both can coexist easily in a simple manner, right? This is about the word equilibrium. Now, what is this word phase? What is a phase? If I ask you to define a phase, what do you define? Anybody? Anybody want to take that? What is a phase? You can type in the chat box, or you're happy to unmute and actually, talk. Anybody want to? Okay, fine. No worries. Yeah, I think Munal
Yeah,
unmuted. Go ahead.
this is basically one thing which is physically distinct, physically and microstructurally distinct from the others. This unique like that. One phase is just unique of other phase like that. Anything distinct from
Yeah,
others.
so basically, exactly. So there is the proper definition of a phase tells that it is chemically homogeneous. Number two, physically distinct, as you rightly mentioned, that it has to be unique, it has to be distinct, and it has to be mechanically separable. Okay. So chemically homogeneous means what? Within a phase, it is the composition is uniform throughout the phase. That is called as a homogeneous chemically. Physically distinct. That means you need to actually, you know, uh, easily uh, tell it that a phase is a separate entity, and mechanically separable. That means a phase can be separated out using some treatments. Okay. Best examples are solid is a phase, liquid is a phase, gas is a phase. Similarly, within a particular system also, there might be different phases existing, like alpha iron, gamma iron. So these are all different phases. Okay, examples of phases I would say. Okay, now you have to keep in mind that phase is typically, denoted by a letter P, right? So why is it used to us? As I told you, if you have two different phases, A and B, let's say A, B are two different phases, and if you want to show its relationship, what is that relationship? I told you previously, the conditions at which A and B can coexist together, those conditions are well represented by my phase diagrams. So phase diagram is nothing but a graphical representation, okay, explaining about the equilibrium conditions between two phases, or maybe two or more phases also. Okay, so that is the main crux or main fundamental meaning of what is a phase diagram or an equilibrium diagram. Okay, now as I told you, we have an important empirical relationship which actually tells you more information about a phase system, so or a phase diagram. Okay, which is called my Gibbs phase rule. What is Gibbs phase rule? So till now we studied about or understood about what is a phase. Now what is this Gibbs phase rule? Anybody want to take that? Yes, what is Gibbs phase rule? Or maybe what is the equation of Gibbs phase rule? Okay, so let me put it this way. So yes, so Navya has pointed out that we have something called F is equal to C minus P plus 2. Okay. So till now we have discussed only about the phases, which is P, right? P is the phase. Now what is this F and C? Here my F represents degrees of freedom in a system. Okay, that means it tells us what are the variables, independent variables in the system. If you change that, the overall equilibrium relationship will change. Okay, how many such independent variables are there? This number is called as the degree of freedom. Okay, and what is C? C is the number of components. Okay, now what is a component? Component is nothing but it tells you about the independent chemical species that are present in a system. Okay, how many number of independent chemical species? So here I told you I have A and I have B. Okay, so or maybe I can say copper, nickel, alloy. How many number of components are present here? It is two, right? Copper is one, nickel is one. So the number of components is equal to 2. Let's say if I have iron, chromium, nickel alloy, the number of components are 3. Iron is one component, nickel is one component, and chromium is one component. Okay, so depending on the number of components and the number of phases present in the system, the degrees of freedom are decided. Typically, we know, again, I'm talking about the independent variables. What are the variables that we have in our hands? Temperature, pressure, or composition. That means, let's say, 10% copper, 90% nickel is one composition. 50% copper and 50% nickel is one composition. So depending on this composition also, your degrees of freedom changes. Or maybe I can say the equilibrium relationship changes. Okay. So I can write that the possible variables in a system can be temperature, composition, and pressure. Okay. These are the three possible degrees of freedom. Okay, we'll come back to this again, but we also can, we just saw that the number of components are also different, right? If C equal to 1, we call it a unary system. If C equal to 2, we call it a binary system. If C equal to 3, we call it a tertiary system. So that means it is just to classify that, if C equal to 1, we are defining it as a unary system, or the phase diagram associated with a unary system is called as a unary phase diagram. Okay, similarly, if C equal to 2, the phase diagram associated with it is called as a binary phase diagram. When C equal to 3, we call it a tertiary phase diagram. So these are all different classifications based on the number of components available in a system, right? Now, one thing I wanted to ask you is, can anybody tell me a good example of what is, uh, a unary system? Or maybe I can ask you this way: can anybody tell me a best example of the unary phase diagram? Exactly. Water system is a very good example of unary phase diagram. Okay, right. Water is a very good example of a unary phase diagram, which we'll again look at it. Okay, so this is a brief, description of the different types of phase diagrams based on the number of components. Now, coming back to the degrees of freedom, as we already know the number of phases and all we discussed till now. Now, let's try to spend some time on the degrees of freedom. Temperature is okay, composition is okay, but usually metallurgical processes are all actually taking place at a pressure of 1 atmosphere. Okay, that means all the processes that are taking place at room temperature or the normal, room conditions where we have the pressure to be 1 atmosphere. That means you are actually making this constant. And what is the definition of a degrees of freedom I gave you? Independent variable. That means if you change in these degrees of freedom, that means let's say if you change the temperature from 20 degrees to 100 degrees, water is actually boiling. From liquid phase, it is converting to gaseous phase. This is just a simple example. Similarly, the but again, the pressure, if the pressure is constant, you cannot change the pressure. That is what is you are restricting yourself from. Again, this is for 99% of the metallurgical processes. Okay, so what I'm telling you is that you are actually doing this to eliminate pressure from your consideration as a degrees of freedom. So before this, we saw that we have uh, you know either temperature, composition, or pressure can be degrees of freedom. But now, since the pressure is taken as a constant value, it is no more a degree of freedom. That means temperature and composition can be the possible degrees of freedom in a system. Why? Because of this guy, pressure being constant at 1 atmosphere. So to tackle this, we actually have something called as a modified Gibbs phase rule. Why? Because from the given equation itself, you are removing one. So previously, F is equal to C minus P plus 2. But since pressure is removed out of it, you are removing one from it. That means you are subtracting one from it. So what this says is if pressure is constant at this particular condition, what is happening to F? The degrees of freedom F is equal to C minus P plus 1. This is called as my modified phase rule, or it is also called as my condensed phase rule. Okay, why? Because the pressure is constant, there is no chance of gases coming into this. So the condensed phase diagrams typically contains the solid and liquid. There is no chance of gas coming into this. Why? Because the pressure is constant. And we know if the pressure is constant, the available gases in the system is not changing at all. Right? This is called as a condensed phase rule. Okay. Now, one more question which I wanted to ask you is about what can be the minimum and the maximum possibility of F. What can be F minimum and what can be F maximum? Anybody want to take this? What can be the minimum number of degrees of freedom a system can have? And what is the maximum number of degrees of freedom a system can have? Yes, the minimum degrees of freedom is 0. And the maximum is basically a function of your C and P. That means you have to know the C or P, C and P. You need both of them to actually calculate this thing. Okay. Yeah, of course, there are many theories to say that, the maximum would be P into C minus 1 and all. But as of now, we are just focusing on telling it that the maximum number of degrees of freedom for a given system is actually a function of the components and the number of phases present in a system. Okay. Only when you get that, only when you know that, you can find out the maximum degrees of freedom. Okay. Now, so we have discussed about water. Okay. So let me just try to apply this particular rule, Gibbs phase rule, into that system. Okay. Which is, as I told you, example of a unary phase diagram. Okay. What we are taking? We are taking water system. Okay, so we know water H2O it itself is having only one component. Okay, this itself is the one component. That is why it comes under unary phase diagrams. Right. Now, it is always important to see that unary phase diagrams because the number of component is one. That itself will be 100% of it. Water is 100% H2O. Iron is 100% Fe. So typically, unary phase diagrams are pressure versus temperature diagrams. Okay. Why we are removing the composition term? Because this one component itself consists of the 100% composition. Okay. So no need to actually consider that. Okay. And again, P versus T diagrams will look something like this. Pressure on the y-axis, temperature on the x-axis. Okay. And for water, you will see something like this. Okay. This is the diagram for unary diagram for water system. Okay. So somewhere here you will be having water, which is liquid phase. This we have ice, and in this region you have vapor. Okay. So let's say I have a pressure of this much and the temperature of this much. So in these conditions, water exists as a form of vapor, which is steam. Let's say if I have some conditions here that this is the pressure and this is the temperature, then the phase is water. Okay, so depending on the region in which the process conditions are falling into the pressure and temperature I meant, you get to see which phase it is. Okay, and of course, at 1 atmosphere, let's say if you draw a straight line, something like this is 1 atmosphere. Then what are these intersections? What is this temperature and what is this temperature? Anybody? First of all, what are these lines indicating? These lines are indicating the equilibrium between the two phases. Okay. So as I told you that this particular condition will have ice. Similarly, any point on these lines are representing equilibrium between any two, existing phases. That means this particular condition is an equilibrium between ice and water. So both will be coexisting along this plane. Similarly, this ice and vapor. Similarly, this is water and vapor. So everything would be, actually uh, coexisting on these lines. Coexisting in the sense it represents the equilibrium. Now asking the same again, what is this particular temperature at 1 atmosphere pressure and what is this particular temperature at 1 atmosphere pressure? Carefully observe what this is. These are the equilibrium lines and this is at 1 atmosphere. So what are these temperatures? Or quickly maybe you can see this what is actually happening at this point and what is actually happening at this point. Yeah, anybody? Yes, I can see few people typing. Let's get their answers. Cool, exactly. So Ratnesh says these values are 0 and 100. This is my 0 degrees Celsius. This is my 100 degrees Celsius. How I can tell this? Very easy. So at 1 atmosphere, that means we are at room temperature. I mean, I mean to say room conditions. So at this point, what is happening? It is equilibrium between ice and water. That means that can be a freezing point, correct? So this guy, of course, the melting point. So this is my 0 degrees Celsius. Similarly, at this point, what is happening? This in equilibrium between water and vapor. What is it? It is nothing but the boiling point. This is the boiling point. This is the melting point. So that is why this is 0 and this is 100. Clear? Did you get it? Why or how I got these values? I ended up with the values of 0 and 100. Cool. So, the next thing, of course, is nothing but looking at this particular important point, which is called as my triple point. I'll just bring that out of the diagram. Triple point. That means you can see that all the three phases will be coexisting at this particular point. So I can say that the degrees of freedom is equal to 0. How I am telling that? Because if you just change the pressure by a bit or a temperature by a bit, what happens? That the condition is actually changing out of the triple point. It may go this way, or this way. So from the three phases, you are going into a different region. That means the triple point is only existing at one given pressure and temperature combination. If you change anything, you cannot actually see that. That is where you see that the degrees of freedom is 0. Or how to calculate that? Very easy, right? Let's put our uh, modified rule here. C minus P. Of course, I cannot do the modified phase rule. I should use the Gibbs phase rule because pressure is here. It is not a condensed state, right? So if I want F, I can write C is equal to 1 minus P plus 2. So I got an equation F is equal to 3 minus P. So at any given point, based on the number of phases, the number of degrees of freedom will change. So as I told you, at this point, at the triple point, all the three phases will be coexisting. That means P is equal to 3. So I can write this right at triple point, P is equal to 3. That means F is equal to 3 minus 3, which is 0. Similarly, if I take some point somewhere here A, at point A, how many phases are coexisting? Can I get an answer? How many phases are coexisting? Two, yes, because the two phases are in equilibrium, ice and water. So, here what would be my degrees of freedom? F is equal to 3 minus 2, which is 1. F is equal to 1. You can either change only 1 if you want to actually maintain uh, you know the same equilibrium. That means only even if you change one, the other is actually getting changed. That's what it is meaning. And if you are somewhere in this region, in a single phase region, I can say that means at point B, P is equal to 1. That means F is equal to 3 minus 1 is 2. That means you have the flexibility to either change temperature or pressure within this particular region. You can change anything. Okay, but you can't do that on this line or at this particular triple point. Okay, this is actually how you will be using the phase diagrams and slowly get information about the phases present depending on the conditions, or you actually get that by using this mathematical expression which is called as my Gibbs phase rule. Okay. So yeah, maybe I'll upload the video on YouTube. So no need to worry. I mean, no need to take screenshots and all. It will be uploaded on YouTube. Okay, very soon. So don't worry about that. Okay. Yes. So people, I see people still joining. So if anybody joined the conversation soon, I mean, just now, you can always join the call in order to access the demo session. Okay. Right. So one thing before moving on, I wanted to leave you is that I want you guys to go and study the unary phase diagram, which is the PT diagram of iron, right? So iron, we know alpha, gamma, delta, there are different phases present in it. So what I want to do is just go through this and try to understand how iron PT diagram looks like. Okay, this is one thing which I wanted to leave you guys with. Okay. Similarly, quickly we'll look at the binary phase diagram, and then we can, move on to the second topic for the demo session. Okay. Yeah. So I got a question here. So the temperature of the triple point. So these are, standard values. So as I told you, because the F is 0, these has to be fixed values, right? It is 0.01 degrees Celsius and 0.006 atmosphere. Okay, these are fixed values. The triple point has 0.006 atmosphere pressure and 0.01 degrees Celsius temperature. Anything else? Anything else from this thing? From the unary phase diagram? Okay, so quickly let's move on to the binary phase diagram. So clearly, from the classification itself, you have to know that C equals 2. When the components are 2 only, we call it a binary, right? So here it is important to actually see how you will be using it. So as I told you, temperature, pressure, and composition, and one is ignored, which is pressure. Why? That there is one more reason for this. Because if you want to show the effect of temperature, pressure, and composition, you basically need a 3D plot, which makes our life difficult, right? You actually cannot put it on paper very much easily. So to avoid that confusion, and because of the fact that most of the metallurgical processes will be happening at I mean, at a pressure of 1 atmosphere, you see that the pressure is ignored and you get temperature concentration plots. Concentration or composition, whatever you want to call. Okay. So what you're doing it, you are ignoring the pressure effects. Okay. As we have discussed. Okay. That means here it is a condensed phase diagram. So there won't be any vapor phase. Vapor phase will not be present. Okay. This is an important thing. So here what is the Gibbs phase rule that is used? The modified one, C minus P plus 1, because the pressure is ignored. Okay, this is the modified phase rule. Okay, so quickly again, it will be T versus X curves. Okay, X, or usually people write in terms of weight percentages. Okay, so the composition can actually be, I'll write it out. composition can be usually represented in two ways. One, the weight percentage of a particular solute atom, or you can also use atomic percentage. Typically, we use percentage weight. Okay, so let's say you have an AB alloy. So here percentage B we are writing. That means here this is 100% A or 0% B. And similarly on the other end, what you have? Other end you will be having 100% B. That means 0 percentage A. Okay, this is how your concentration will look like. I mean, look like in the sense because of the way this is actually doing it. Okay, so as I told you, the composition, you know, can be put in terms of weight percentages and atomic percentages. It would be nice if you have a simple conversion formula. So you basically have it, right? So if you want to get an atom percentage of A, this would be written as the weight percentage of B, 8% of A divided by the atomic weight of A divided by the cumulative thing. That means the weight percentage of A by atomic weight of A plus weight percentage of B by atomic weight of B. Of course, because it is percentage into 100. Okay. So this is a very, very easy formula one can use to convert the atom percentage to the weight percentage or vice versa. Okay. So this is about, of course, there is ternary phase diagram and many more into this, but I'm keeping it simple for you guys for the demonstration. So this is my first topic. So what we've discussed what is a phase diagram, and uh, what is Gibbs phase rule, and then we saw slowly how we can use the Gibbs phase rule in the unary binary phase diagrams. Okay, any doubts till now? Anything that you wanted to, you know, cool. If not, we'll move on to the second part of the demo session, which is our Mohr circle. Okay, so till now we saw about topic from physical metallurgy, which is phase diagram. Now let's move into Mohr circle, which is a topic from mechanical metallurgy. Again, this is a topic which is asked by many of you guys, so that is the reason why I wanted to put this up. Okay, so let us try to understand first. Okay, so this is from mechanical metallurgy. Okay, so let us try to see in this way. So typically any body there are two type of stresses possible. What are those? Either normal stresses. Normal stresses means they basically the stresses which are normal to the planes, normal to the surfaces, or perpendicular to the surfaces. And these are represented by sigma n. And you also have shear stresses. Okay, is denoted by tau. Now, what Mohr circle does is, again, this is also a graphical representation, but it represents the state of stress. Okay, it is a graphical representation of the state of stress on any point. Okay, any point of a plane. Usually people like to call it an oblique plane. Yeah, so if you have an inclined plane and you have a point on that, what is your state of stress looks like? Okay, how normal stresses are acting on it, how the shear stresses are acting on it, all this can be understood with a simple graphical representation, with a simple circle. In the name itself, we have right Mohr circle. Okay, that graphical representations looks like a circle. Okay, so maybe I can show you this particular you know state of stress. Let's say I have a very thin plate. Okay, and I am applying a normal stress sigma x and sigma y. Okay, and I also apply a shear stress. Okay, so this is my tau xy. This is my tau yx. Okay, so before that, what is this xy and yx? Typically, the shear stresses are represented by something called as tau ij. What is tau ij? Can anybody comment on this? What is tau ij? So basically, it is representing a stress that is acting on a plane that is perpendicular to this I axis. Okay, acting on a plane which is perpendicular to the I axis. Okay, I is nothing but this I which I have here. And in what direction? In the direction of J. The direction of J axis. This J. Now carefully try to relate what I wrote here. Tau xy. That means it is actually perpendicular to the x plane, correct? This is my x. In the direction of what? In the direction of y. This is x axis, this is y axis. You can see that this is actually perpendicular to the x axis and it is acting along the y direction. So tau xy is what it is called. Similarly, this guy also you can see this is perpendicular to the y axis and it is acting in the x direction. So tau yx. Because this is what typically people tend to represent. Now, if I have, if I choose a small element in this particular plate, okay, and this is the oblique plane which I'm talking about. Okay, on this oblique plate, there are obviously a shear stress acting on that and a normal stress acting on that. Are they equal to sigma x or sigma y or tau xy? No, because of the angle. It is an inclined plane. Let's say this angle is theta. Okay, and of course, in Mohr circle we use 2 theta for a theta in a physical state. Okay, don't worry. Again, I'm not going in detail about that now. Discuss more about that in the full course. Okay, so what is our motto is actually try to study these guys, the value of sigma and tau, and how you can represent on a circular fashion, which is the Mohr circle itself. Okay, you can see now graphical representation of a state of stress on any point of an oblique plane. So here you see this is a point that we have on this oblique plane, and you want to actually represent these state of stresses, which is tau and sigma n. Okay, so again, I'm not actually deriving it now due to time constraints. I'll directly give the value for that. So if the plane is with the theta in physical state, then sigma n would be equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 times cos 2 theta plus tau xy times sine 2 theta. Okay. Similarly, tau can be written as sigma y minus sigma x by 2 times sine 2 theta plus tau xy into cos 2 theta. So these are the two equations. So this is equation 1, this is equation 2. Now what usually we do is we take this term on the other side. Again, as I told you, I'm not deriving it now. But yeah, due to simplification, I directly gave the values term. Okay. So if you take this term on the other side, what this becomes, I can write this sigma n minus sigma x plus sigma y by 2 will be equal to the other term. Correct? What I did, I just took the average of these two from RHS to LHS. That's all. Everything is same. Now, what you have to carefully observe is you have two equations 1 and 2. If you do 1 square plus 2 square, you will be getting a equation in the form of a circle. That is what is the that circle actually has the sigma values, tau values, and all. Okay, so what it will actually look like? So this would be sigma n minus of sigma x plus sigma y by 2 whole square plus tau square will be equal to on the other side, because you have various sine 2 theta cos 2 theta, when you are squaring and taking common and all, they get vanished out, and you will be left with sigma x minus sigma y by 2 whole square plus tau xy square. This is what you will be left with. Again, I'm not going into the derivation of it. Okay, so this is looking like something like x minus x1 whole square plus y square is equal to some r square. Correct? This is my simple form of a circle with center as x1 comma 0. So basically we write y minus y1, but because we don't have any term y1, I directly wrote like this. Okay, so typically this is the form, right? X minus x1 square plus y minus y1 square is equal to r square. So this has a center of x1 comma y1. So here y1 is 0, so I wrote x1 comma 0. And what is x1 here? This guy. This is my center. So I can write the center of the Mohr circle would be equal to the average sigma x plus sigma y by 2 comma 0. This is the center. I can basically write sigma average comma 0. And if you see carefully, this circle lies in the xy coordinate space. Similarly, here, if you see, what is x here? Sigma n. What is y here? Tau. That means this circle will actually be in the space of sigma n and tau. So sigma n, which is my normal stress, will be on the x-axis, and the tau will be on the y-axis. Okay. So now the circle, this particular circle, will actually lie on something like this. Tau on y-axis, sigma n on x-axis, and you have some circle like this, which is my Mohr circle. Okay, so if you take at any particular theta at any point, what is sigma n, what is tau, you can easily find out. Okay, but yeah, so before ending here, I'll quickly tell you how can you plot these Mohr circle easily. Okay, so what I'll do is I'll quickly bring the same plot so that it will be easy for both of us. Okay, yes, this is what is the state of stress that you are looking at in a plane stress condition or a very thin plate. What you're looking at is just taking that, taking an oblique plane, and you want to study the value of stress on these things. Correct? That's what you want to study. That's what you are interested in, right? So now, again, you need to take 2 points in order to plot it, right? So let me take one point over here and the other point over here. Let me name this point A and name this point B. So what is step one? So basically take the coordinates A and B. Okay, so A, what is coordinates again? Remember, x-axis is sigma, y-axis is tau. So what is sigma acting at point A? Sigma x. comma tau xy. So typically we take minus tau xy. Why? Because the shear stress which is causing a clockwise rotation is positive. Here, if you see, this is actually creating an anti-clockwise momentum. So this at point A, the tau xy is considered negative. Why? Because of its anti-clockwise momentum. Whereas at B, you see, this is in a positive direction. That means it is in a clockwise rotation. So B is actually with a normal of sigma y, and it is plus tau xy. Okay, you understood how we took that? If you have a shear stress producing a positive or a clockwise rotation, it is taken as a positive value. If it is creating an anti-clockwise momentum, it is taken a negative value. Very easy. Okay. So and then plot them. So let me take the axis for you. Okay. So this is tau. This is sigma n. And so you see negative y-axis, right? Point A. Point A is somewhere here, which is sigma x comma minus tau xy. Similarly, point B is somewhere here, okay, which is sigma y comma plus tau xy. This is the first step that you want. Now, what is the second step? Join these 2 points, okay, and obviously the midpoint of these two will be the average, which is the center of the circle. Correct? That's what we studied previously. What is the midpoint of these two? Sigma x plus sigma y by 2, and the other term will be 0 because minus n plus. So now it is very much clear that the center of AB, or the midpoint of AB, lies on the x-axis, which is acting as a center, and this AB is my diameter. So now what you need to do next is just take point C as center and CA or CB as diameter. Just draw a circle. This is my circle. Okay. Yeah, of course, I did not draw it much accurate, but let me do that. Okay. So this is my point A, right? Again, as I told you, this makes sense. So here we have two important values which are called the principal stresses, the maximum and the minimum normal stresses acting. Okay. Similarly, what is the maximum shear stress? Maximum shear stress you can see is nothing but the radius itself. Why? Because this would be with the maximum tau value. Okay. So the radius that you see on the RHS is nothing but the maximum shear stress a particular plane can observe. Okay. And of course, I told you this angle is 2 theta, right? So on the physical material, the angle is theta, but on the Mohr circle, the angle would be 2 theta. Okay. So you can easily see that sigma 1 and sigma 2 is actually equal to, what can I write? Sigma average plus or minus r. Or in other sense, I can write this as, let's say this is OC plus or minus radius. Okay, so O is the origin, C is the center. Okay, and again, R we already know. I can write sigma average plus or minus tau max. So this is a simple way to actually calculate the principal stresses from the mode circle. Otherwise, you need to actually have big equations, and you need to understand the derivations in order to go ahead. Okay, this is a pretty easy way to actually see how uh, at a given point we can find out what are the average, I mean, what are the principal stress values. Okay, any doubts, in the Mohr circle? So this is how you need to calculate the Mohr circle. And one more important thing is I want you to actually go and draw more circles for a different 2D and 3D cases. Okay, uniaxial, biaxial, triaxial, where sigma 1 equal to sigma 2, sigma 2 equal to sigma 3. So take different conditions and try to draw them. Okay, so two tasks for you guys from this particular session. One is to understand the PT diagram of an iron system, and now understand the Mohr circle of different conditions, different, you know, 2D and 3D cases that you will find across. Okay, so that's it from my end. If you have anything, you can always, type in the chat box or unmute and talk. Okay, so again, putting it out here, the classes are starting from March 14th. So, make use of it. The next 1 year would be of a great learning curve. And I hope this helps everybody of you. Okay. So looking forward for, most of you to join with us and, you know, continue their journey towards cracking gate metallurgy. Okay. So that's it from my end. Let me stop the recording.